Analysis of deformation in a real arteriovenous fistula in silico study. Introduction. Arteriovenous fistula (AVF) is indicated by some as the most recommended vascular access VA for treatment hemodialysis. However, even though the access is best recommended, some problems can make it unusable. It was observed that about 16% of AVFs do not reach the ideal state of use after their conception. After the creation of the AVF, there is a variation in the flow condition of the system, especially in pressure and flow, and these changes are important parameters with regard to maturation and access conditions. The variation in flow conditions have a direct influence on the vessel composition and consequently on its rigidity. The structural patterns of blood vessels related to the deformation or rigidity of the vascular wall are fundamental importance to analyze and determine the conditions of the fluid dynamics behavior of the AVF. The present work analyzes the deformation of a flexible AVF model as a function of pulsatile flow, correlating this parameter with the flow and morphological conditions of the VA. Methodology: data acquisition and processing. The three-dimensional reconstruction of the AVF was performed using a computer tomography (CT) scan of the left upper limb of a patient with a brachycephalic arteriovenous fistula performed at the Onofre Lopes University Hospital of the Federal University of Rio Grande do Norte. After the three-dimensional reconstruction of the AVF, the correction of some open elements of the generated virtual solid was performed and structural geometric elements were added to collect the pressure values points 1, 2, 3, 4, and 5, and extensions at the entrance and exit for the attachment of the experimental bench pipes. AVF manufacturing. After the acquisition and improvements of the AV geometry, a split and made mold internal volume was developed to manufacture the flexible AVF Figure 3. The mold and the internal volume were developed based on the AVF model extracted for the patient using the Fusion 360 software. It was later manufactured by additive 3D print with 100 filling ensuring the rigidity and precision required for the manufacture of flexible AVF. Figure 3 shows the schematic of the mold and internal volume development. Experimental procedure. For the procedure, an experimental workbench Figure 4 that simulates the pulsatile flow developed in previous works, and a video capture system were used to accurate the geometric variation of the system as a function of the pressure pulse implemented in the system. The regions chosen for the analysis of the deformation were chosen located in points 1 and 2, located in the arterial region of the vascular access, and in points 4 and 5, pseudoaneurysm resulting from the drives for the treatment, located in the region venous vein of the VA. Results and discussions. The first result of the work was the flexible AVF Figure 6, manufactured from the split model and the design and manufacture internal volume. It is made of a commercial silicone from head leaves and has a constant thickness of 2 mm. Superficial and internal inconsistencies in the systems were observed during the manufacturing process, such as the presence of bubbles and variation in thickness, which were corrected with the correct centralization of the internal volume in the mold. After the creation of the AVF and implementation of the pulsatile flow conditions in the system, the pressure values at the inlet and outlet of the VA were observed. Figure 7 shows the pressure values as a function of the normalized time at the flexible AVF output and input. Analyzing previously the pressure pulse in Figure 7, it is observed a damping in the average peak values of the exit pulse in relation to the entrance pulse, mainly related to pressure loss due to friction and deformation. The main pressure values observed during the experimental procedure were 14.397 kPa and 4.651 kPa at the entrance and exit, respectively, observing a drop of 9.75 kPa, equivalent to 67.7% of the initial value. Another parameter of the analyzed flow was the system flow, where mean values of 1325.5 mm per minute with a peak of 1493.07 mm per minute. We observed a result consistent with rates observing patients undergoing hemodialysis treatment. Through the analysis of the deformation at different points, it was evident that the regions with the highest deformation of the system were the location of fistula neuritis point 4 and 5, with peak values around n 0.303 at point 4 and 0.237 at point 5, figure 8. The reason for these points to present the greatest deformation was the larger dimensions cross-section area in relation to the other points mentioned. System deformation does not only take into account vessels wall thickness values or mechanical conditions of the system, but also cross-section area as evident by right pressure values at larger points. Conclusions: the results present show that the elasticity of the system and consequently its deformation has a direct influence on the flow conditions of the system, such as pressure and flow. Therefore, considering the study models as rigid will not present satisfactory results or consistent with reality. Another important point is the different elasticity of the material and the composition of tissues that make up blood vessels, which must be thoroughly investigated for a better understanding of the general phenomenon. It is worth emphasizing the importance of this study for improving the quality of life of patients with AVF and undergoing hemodialysis treatment. Acknowledgement: I would like to express my thanks to the financial support of the Coordenação de Aperfeiçoamento de Pessoal do Nível Superior Brasil CAPES Financing Code 001. Reference: I would like to thank everyone for their attention and apologize for my diction in English pronunciation. Questions?